Crystal field theory. See, it's an electrostatic model of explaining the formation of the coordination compounds. Why we call it an electrostatic model or electrostatic way of explaining the formation of the coordination compound? Because this theory regards the forces of attraction between ligands and the central metal ion completely electrostatic in nature. They regard ligands as the point charges and the forces between them completely ionic in nature. Now, according to this theory, which explains the formation of octahedral, tetrahedral and square planar complexes, but we have since only explanation of the octahedral complexes in our syllabus. I am taking only that one. So let us see what happens in these cases. We know the octahedral complexes or entities will be having a general formula of Ml6, where 6 ligands will be attached to the metal ion. Now, when all these 6 ligands can be arranged around the metal ion like this. Now, they all are present at 90 degrees to each other. Now, as seen from this diagram, it is very clear that they all are present along the axis. So what happens is, during the formation of any coordination entities, the ligands approaches the metal ion and they are always approaching along the axis. So they are having direct head-on collisions with those orbitals which are lying along the axis. That is why what happens is, their energy gets increased and the energy of the other orbitals gets lowered, which are lying in between the axis. And this is how the splitting of the d orbitals takes place. Let me explain it to you like this. Like, if suppose these are the 5 d orbitals we are having, 2, 3, 4, 5. Now see, this is a degenerated level. We call it ground state, because these d orbitals 5 all are having same energies and all are at the ground state are having same equal energies. When the complex is about to be formed, the energies of this metal ions d orbitals gets increased, so they reaches here at a higher level like this. Now these still are degenerated, means all are having same energies, but we call it as excited state. Now we know out of these five, the first one dxy, yz and zx. These are present in between the axis, whereas dx square minus y square and dz square is present along the axis. So these two orbitals which are present along the axis, they get a head-on overlapping or collision with the approaching ligands. So their energy gets increased and so they reaches to a higher energy level, whereas the energy of these 3 orbitals which are lying in between the axis, their energy gets lowered, so they acquires lower energy like this. So the d5d orbitals now becomes generated. They splits up into 2 parts. The lower part is called T2g orbitals, which is having dxy, yz and zx, and this is called Eg, higher energy level, which is having dx square minus y square and dz square. So this is how the d orbital splits up into T2g and Eg levels. The energy difference between these two is called delta O. Specifically in this case, this delta O is called crystal field splitting energy. It's called CFSE in octahedral complexes. So this small O written as subscript indicates that it is an octahedral complex. So this is how this splits up. Now remember, this height is more, the splitting is more. This is about 0.6 or it is 3 by 5, and this splitting is about 0.4 or 2 by 5. So this is how the total average energy remains the same, and this splits up into 2 parts. This is what is the diagram we have of a splitting up of the d orbitals in octahedral complexes. Now what happens is, see, according to this CFT, that from D1 to D3, we don't have any options or any problem of whether the pairing of the unpaired electrons takes place or not. Because if suppose we have even a D3 configuration, the 3 electrons will definitely, as per Aufbau principle, will occupy the lower energies. But now the moment we have D4, so from D4 to D7 or D6, we have different possibilities. Like what happens is, like then if we have suppose a D4 configuration, a D4 ion is there, then where this fourth electron goes in these T2G and EG orbitals. Now this is being decided by the magnitude of the splitting energy. See, there is one more energy involved in this, which is called P, called pairing energy. Pairing energy is the energy required to pair up an electron with another electron in an orbital. So the energy required to pair up the electrons in an orbital is called pairing energy. Now what happens is, that is what the CFT tells us, that from D4 to D7 we have two options. There are two options. The first option is, if pairing energy is more than the splitting energy. If pairing energy is more than splitting energy, it means what? Suppose your splitting energy is of your approximately say 30 kilojoules per mole, and the pairing energy is basically 40 kilojoules per mole. So in place of spending the 40 to make them paired here, what will happen is the fourth electron will be given a 30 kilojoules of energy so that it enters here. So in this case what happens is, no pairing of electrons takes place in this case. Whereas the second option says, if pairing energy is less than splitting energy, it's very high. Suppose this splitting energy is about 80 kilojoules per mole. So in place of spending 80 kilojoules to make that transfer the electron, fourth electron to this EG level, what will happen is it will be paired here only. So in this case what happens is, pairing of electrons takes place. So what happens is, so we have two options. When the splitting energy is greater than the pairing energy, pairing takes place. When pairing energy is less than more than the splitting energy, no pairing takes place. And that is why we can easily distinguish what I can show it to you here. Therefore, the D4 configuration here will be written as T2G3 EG1, whereas in this case it will be written as T2G4 EG0. Similarly, the D5 will be written in this case as T2G3 EG2, whereas in this case it is written as, how we will write it down? It will be written down T2G5 EG0. D6 will be written as T2G4 EG2, whereas D6 in this case will be T2G6 EG0. So this is how we have the two different cases where the pairing is taking place, and in this case no pairing is taking place. So this is what is the basic differences. Now when the pairing will take place and when the pairing will not take place, it depends on the magnitude of the crystal field splitting energy, and it is being decided by the nature of the ligand. Stronger is the ligand, the more stronger the repulsion it will cause to these T2D EG orbitals. So the higher energy they acquire, greater will be the magnitude of the splitting energy. So therefore in all those cases always a pairing takes place. So remember, the pairing of unpaired electrons is directly proportional to strength of ligand. How strong the ligand is. If the ligand is very strong, it will cause more repulsion, and that is why we can have a higher magnitude of CFSE, and that is why we can have this kind of a behavior. And on the basis of this, slowly we calculated the magnitude of these splitting energies, and we came out with a series of in which the elements or the different ligands were arranged according to their decreasing order of their splitting energy values, and this series is called, we call it spectrochemical series. So what is spectrochemical series? It's a series in which the ligands are arranged in the decreasing order of their CFSE values. Now in this case, the most important becomes your carbon monoxide, then becomes your cyanido, where the carbon is the donating atom, then ethylene diamine, then we have ammonia, then we can have more isocyanide, then we can have in this case oxalato, then we can have OH minus, then we can have even water comes before this, because water definitely we can have here water OH minus, so like this, so on, and then we can have the halogens I minus, Br minus, Cl minus, F minus, so like this. So all these are, this is what is a spectrochemical series in which the ligands are arranged in decreasing order of their spectrochemical power. Now what we find is the strength of the splitting energy in these, the value of the magnitude of the splitting energy decreases from here to here. The better the donor we have, they're like carbon, so the greater is the magnitude of the splitting energy. So in all these cases what we find that the pairing takes place. So this is what we have, the splitting of the d orbitals in case of octahedral entities.